All right, let's get started. Before we do, does anybody have any questions? All right, we'll follow the same format as we did yesterday and continue on with our discussion on subsurface flow. And today what we will do is, having at least reviewed Darcy's law and the idea of transmissivity and so on, we can start with just a minute. Just a minute while my
Oh, fine, sir.
Okay, so today we will start with looking at the general equations of groundwater flow. Then we'll talk about how we can specialize it to some, cases of confined and unconfined aquifers and simpler cases. And in the second half, we will talk about unsaturated flows. So in this particular slide, we are looking at a block of soil. It has size of delta x, delta y, delta z, the 3 dimensions along the x, y, z coordinates. And we will define the piezometric head at this location. And we will use small h to denote the total piezometric head. So it can be a function of x, y, and z, the 3 spatial dimensions, and also time. And when we try to derive the general covering the equations in Euler frameworks, we essentially choose this as our control volume and talk about the ways in which water can enter the control volume to all the control surfaces. And so the inflow rate, basically in the x direction, x is this direction, so flow coming in, according to Darcy's law, is going to be the hydraulic conductivity, the gradient of the piezometric head times the area through which it enters with a minus sign. Similarly, the outflow rate is essentially as water is moving from this location to a distance which is the small delta x away in the x direction. We will look at how fast k del h del x changes in the x direction. So we have k del h del x plus how fast it changes over x times delta x. And then that is also coming out through an area of delta z, delta y. So the inflow volumetric flux of water in the x direction, this is the outflow. Their difference is the net inflow of water coming in the x direction into the control volume. And if we were to write similar expressions for water coming in for the y and z directions into the control volume, these would be our expressions for the net volume of water that is entering the control volume. These are the flow rates. And if in a small time delta t, we want to know how much water is therefore entering the control volumes, we have all these flow rates coming in, and we have multiplied those by the areas, and then we have multiplied by delta t to indicate the time as well. If you are withdrawing water out of the control volume, and let's say the withdrawal rate is W, so that is the volume of water we are removing per unit volume of bulk volume of soil per unit time, then that is the rate, this is the volume, delta x, delta y, delta z times delta t is the time over which we are removing this water. So this is the volume of water that's being extracted, at least in our sign convention. So W is positive if I am removing water. So we had certain amount of water coming from the sides, we have removed certain amount of water, and by definition, we have defined something called specific storage. Specific storage is the net volume of water that is being added or removed from a unit volume per unit change in physiometric head. So, Can you hear me now?
Yes.
All right. So continuing along then, by definition of specific storage, which is the amount of water that is released per unit volume per unit change in piezometric head. So that is SMS, specific storage, the volume that we have for the control volume is delta H, for delta X, delta Y, delta Z. And let's say over the small time delta T, the change in piezometric head is delta H. Then this is essentially the volume of water that has been added in the storage. So our volumetric balance will then say, this is the amount of water that's entering in time delta T. This is the amount we have removed. So this is the amount that we have added into storage. And so we are going to try and equate all these. And then in the limit, we think of all these delta X, delta Y, delta Z, and delta T all going to 0. We're going to try and make them pretty small. We'll divide throughout by delta X, delta Y, delta Z, delta T. And therefore, we will get this continuous form of the governing differential equation. So we talked about the idea of representative elementary volume, where we said that we will make these infinitesimal volumes go to 0, but still at the scale where properties like the conductivity and in fact the porosity also, that we can take derivatives. So this is our general governing differential equation. And so this is what we use or specialize for different applications when we try to deal with porous media flow. The question that we also briefly addressed is if it's a confined aquifer. Confined aquifer, it has confining layers both on the top and the bottom. If we are going to be withdrawing water with specific storage, where is the water coming from? And unlike an unconfined aquifer where there's a water table, you can visualize the water table has been lowered. So within this pore space through which the water table has been lowered, part of that pore water is available to be withdrawn. But in a confined aquifer, it was saturated before, it is saturated even after the water withdrawal. And the water, therefore, is coming out from what we call as compressibility effects. We consider that water, everything is compressible, but the soil particles are far less compressible than water, which is already fairly incompressible. So what we are expecting is that the water is going to be compressible. So if I try to remove some water, the volume of water is going to essentially be ready, so it will expand. So that is going to yield some of that water. Plus, as we remove the water, some of the pressure that was being shared by the water is now going to be transferred to the solid soil skeleton. So the solid soil skeleton, the entire aquifer as a bulk will compress a little bit. The solid soil particles themselves are not going to compress, at least because they are relatively incompressible. But overall, the particles will arrange or rearrange a little bit so that you have a small amount of compression. And that is where the water is going to come out. So last class, somebody talked about subsidence, where that come from. So if this readjustment of the aquifer happens to be very large, then we will have soil subsidence. And then we have to, as I said, there are theories for that. We have to do a few changes to our governing equations to account for subsidence and also allow for the fact that in this case, the soil particles are actually moving as well a little bit. But either way, the two important things are going to be compressibility of water. That's going to allow some water to be released. And compressibility of water is defined as change in volume of water divided by original volume of water for change in pressure. The minus sign to indicate that as pressure increases, the volumes decrease. So this basically, as long as these changes in volumes compared to the original volumes are small, there is an elastic region. That means it's essentially reversible. If I remove some water, water pressure is going to go down, water will expand. If I try to push some water back, then water is going to be compressed, and therefore its pressure will increase. And so we assume that both things can happen. Similarly, there is compressibility of the bulk aquifer itself. So if the compressibility is going to be porosity, again, you will have a similar definition for compressibility. Change in total volume of soil divided by the original volume, bulk volume, divided by the change in stress borne by the soil particles. But these are compressibility definitions. So if we were to increase, so the moment we start drawing water, let's say to pumping activity, so in the neighborhood where we are trying to remove water, as water starts to come out, we have reduced the volume of water. So water will expand to fill up that space. And in doing so, the pressure of water will go down. We have removed some of the water, water has expanded, its pressure has gone down. So that this excess change of pressure is transferred to the soil skeleton, which then wants to compress. The soil particles themselves don't compress, but the aquifer rearranges a little bit, soil particles rearrange, and therefore there is a compression in the bulk volume of the porous medium. So these two things combination is where the water is coming out of, or from storage or for confined aquifers. So this is the idea of storage, and of course we talked about unconfined aquifers. And yesterday in your tutorial problem, you saw that, well, if the water table is changing over a certain height, not the entire pore space is being drained. The fraction of that is being drained is what we have called a specific yield, for instance. Because some of the water is going to be held very tightly by the soil. It's not going to release all of that water. So specific storage, and it can be shown, it takes a little bit of algebra to show that this specific storage is going to be related to alpha and beta, which were the compressibility of the porous medium and the compressibility of water. And eta is the porosity, G is density, and rho, G is gravity, and rho is density. S sub S has dimensions of universe of length. It is volume of water divided by bulk volume of soil divided by unit change in piezometric F. We define transmissivity, if you recall, which essentially talks about the ability of the aquifer to transmit water throughout its thickness. And if the hydraulic conductivity is constant and the aquifer thickness is small b, then transmissivity is k times b. Then this becomes an aquifer property. Similarly, if I have specific storage, and if I multiply the thickness of the aquifer, then now I can talk about volume of water that is used per unit area of the aquifer, but throughout the thickness of the aquifer. And therefore, if I multiply this quantity S sub S by B, S, which is aquifer storativity, now becomes an aquifer. So if you are dealing with essentially horizontal flows, and we use properties of transmissivity and aquifer storativity, now these are considered to be bulk aquifer properties. So let's look very briefly at what these equations are going to be like for some simple cases. So here we have two-dimensional horizontal flow, essentially horizontal flow in a confined aquifer. So this is the confined aquifer over here, has a thickness of small v, and the piezometric surface of this confined aquifer is given by small h. So from some horizontal reference, the height of the piezometric surface is small h. And let's say W is the amount of water that we are extracting, per unit area and per unit time from the confined aquifer. Then our governing differential equation essentially is going to be multiplied throughout by V. We will have eliminated the variation in the Z direction, and our equation will look something like this. There is a little bit of algebra that one needs to do, but essentially our equation then looks like this, where we now have transmissivity in the X and Y direction. W is now the volume of water that is being withdrawn from the aquifer per unit horizontal area and per unit time. S is aquifer storativity. So you would basically work with this. And notice that for this equation, the advantage is these parameters, the transmissivity in the X and Y direction is not dependent on H. So in sum, what that essentially means is this equation is therefore linear in H. And linear equations are easily solved. In an unconfined aquifer, as we talked about last class, the aquifer is very thick and and the fluctuations in the water table are small, then we are able to approximate it by using the concepts of a confined aquifer. In an unconfined aquifer, if I were to use the same process, then I would have an equation like this, where essentially things have been averaged out or integrated out in the vertical direction. This is the bottom of the aquifer, and this is the height of the water table. So this is essentially our main aquifer. H again represents the physiometric head, which in this case is the height to the water table from some horizontal reference. And W now is again the amount of water that is being moved from the throughout the thickness of the aquifer. So W is amount of water removed per unit area of the aquifer per unit time. That becomes W. S sub Y is specific yield, capital S is aquifer storage. So these are the storage terms. Then del H del T. So similar ideas. But to be able to write an equation like this, we have already used due assumption. In this case, it's not really necessary. We have assumed that the lower impermeable layer is assumed to be horizontal. There is no leakage. Otherwise, we have to make modifications for, for accounting for leakage or for the fact that the bottom is not a horizontal. The bottom is not horizontal. And you see two terms over here. S sub Y was the specific yield. S is aquifer storativity, which comes from compressibility effects. So even though for unconfined aquifers, we expect most of the water to be coming out of the SY portion. That means that portion of the pore space, when the water table was lowered, that water was removed. However, even for unconfined aquifers, under some conditions, there is a certain amount of compressibility effects also. So we try to account for that, and also we should be cognizant of the fact that S sub Y, the specific yield, which is the amount of water that is going to be released as the water table is lowered, that is not always available immediately. So if you think about the total pore space, this was also a question asked about what is effective porosity. So out of the total pore space, a fraction of it, S sub Y part, is from where you can remove water. The rest of it is essentially not going to be released at all, unless you do something spectacular. It's not going to happen, let's say, in field conditions. You have to bring the soil to the lab and oven dry it to get rid of that portion of the water. So total porosity, therefore, is composed of the S sub Y part plus a part that the soil doesn't release easily. So that fraction that it does not release easily is sometimes called a specific retention. It's retained by the soil. So the total porosity is usually considered as a combination of S sub Y plus the specific retention. Then S for storativity. It's S sub Y just tends to be usually a couple of orders of magnitude larger than S, for unconfined aquifers. So then this becomes our governing equation that we will use for unconfined aquifers. And we would modify it as needed if we had to take care of some other effects like a non-horizontal bottom or leakage from the bottom. We will be able to handle those. Any questions so far? Yes.
In the compressibility part, there is beta or alpha, there is minus sign. Actually, why you are using minus sign?
Okay. Actually, I think you're talking about this minus sign here, right? First, this minus sign is over here, and you will notice it's also over here. Okay. So the reason is, in both cases, when we apply a positive pressure, we expect the volume to go down. So the change in volume dV is negative. So from an original volume of VW, the new volume is VW plus this change in volume, but this change in volume is negative. So to express compressibility as a positive value, we put a negative sign. It's sort of the reverse of elasticity, compressibility. The negative sign is just because we don't want to say the compressibility is a negative number. Otherwise, it just simply because a positive pressure is accompanied by a negative change in volume. So it's just a convention, no other reason. Other questions? Okay. Any other questions? So when we look at this equation now, unlike the confined aquifer, we have the situation where we have conductivity multiplied by H. This was the transmissivity term in the confined aquifer case, but now this term does depend on H. So what that means is this governing equation has become nonlinear. And then it's a little more challenging to work with. May not always admit simple analytical solutions, unless we are able to make some simplifications. The usual form of simplification is to try and linearize the equation, if that works. But there are, some instances where that is possible. As we talked about previously, if the aquifer thickness H is very large compared to the changes that we are going to see in the water table height, we can then use an average value, and basically this term over here, K sub xx times H, we can approximate this by K sub xx times this H bar average value, and think of this as a transmissivity, in which case we would get this particular equation, which now looks similar to a confined aquifer equation. But the fluctuations in the water table need to be small. If Dupuy assumptions are valid and fluctuations are small, then the unconfined aquifer can be, let's say, reasonably modeled by using a confined aquifer equation, where essentially you are making the transmissivity equal to the conductivity times average thickness of the aquifer. So this is essentially one form of linearization. K times H, which was causing the nonlinearity, we are replacing that with K times a constant value of H and calling that as your transmissivity. For steady flows, so if we go back to this equation, steady flows means the right-hand side is 0. Then we notice that we have terms like H del X or H del H del Y, which is actually becomes, 1/2 of d of H squared dx or d of H squared dy, and therefore it becomes linear in H squared for steady state problems. So if we substitute, let's say phi, call that as H squared, then of course dphi dx has 2 times H dh dx. H dh dx or H dh dy is what we have in the equations. So we essentially can rewrite the equation in this form. The value of half will essentially come out, but now the equation is linear in H squared, which is phi. And then of course we can solve for it. Okay. If fluctuations are large, changes in water table height are large in terms of relative to the thickness of the aquifer, so they're not small. And if the flow is unsteady, that means there is the right-hand term with del H del T, then one can still go ahead and linearize, but you have to expect that your linearization is not going to be close to the, close to the solution to the nonlinear equation. So it's unlikely to be accurate. Let's look at a 2D horizontal flow in a leaky confined aquifer. So let me try and explain this figure here. This is the ground surface. This over here, aquifer 2 is your main confined aquifer. Aquitard is this particular layer that allows leakage. So on top of this semi-pervious layer, the aquitard is another unconfined aquifer, which is what has been called as aquifer number 1. So for the main aquifer over here, when it is clean, the water level rises to a certain height, and that height, let's say the bottom of the aquifer is our reference, is small h. So the piezometric head for the main aquifer is small h. The water table height for this unconfined aquifer on top from the same reference is given as capital H. And in this particular figure, you will notice that capital H is higher or larger than small h, which means the piezometric head on the other side of this aquitard is more than what it is in the main aquifer. So we expect leakage to be occurring into the main aquifer. And then of course we have to be given properties of the main aquifer, like its transmissivity and its storativity. So S sub L is storativity of the lower confined aquifer. T sub xx, T sub yy are transmissivities. And from the main aquifer, from the main aquifer, if we are withdrawing water, removing water, again per unit area and per unit time, let's say that rate is WL. We have that, so that is basically removed here. That is present over here, plus the fact that there is some leakage entering into the main aquifer. So that leakage is going to be proportional to H minus small h, capital H minus small h, which is the head difference, as water is crossing this aquitard. So capital H on the top, small h on the bottom. So H minus H divided by C. So C is simply B prime over K prime. B prime would be the thickness of the aquitard and K prime is the conductivity of the aquitard. So this leakage rate is also governed by Darcy's law, but it's occurring in the vertical direction. The head difference is capital H minus small h. The distance through which water is traveling is B prime, the thickness of the aquifer, and K prime is thickness of the aquitard. K prime is the conductivity of the aquitard. Then this becomes our governing equation for the main aquifer. So same ideas, just now that we have accounted for, the physical situation where we have leakage. What we then notice is in this particular equation, we have capital H as one of our unknowns. There is also small h. So capital H was the height of the water table. Small h was the piezometric surface. So in the main aquifer, flow is governed by changes in the piezometric surface. We need to know something about capital H also. And capital H is now part of an unconfined aquifer. So the bottom of the unconfined aquifer, from this reference, say it is at a height of G. And if it's not a horizontal aquifer, then G could be a function of the spatial coordinates X and Y. And therefore, if there is flow occurring in the unconfined aquifer on top, the thickness through which flow occurs is going to be the height of the water table minus the bottom of the aquifer. So that is given by, in this case, capital H minus G. So what that means is, we have two dependent variables, small h and capital H. So we have to write a separate equation now for capital H for the unconfined aquifer on top. And that equation will take this particular form. So it's the same equation now. K is the conductivity, capital H minus G is the thickness through which the flow is occurring. Del capital H del X, that is the gradient for the unconfined aquifer that's moving flow in the X direction. Similar terms for flow in the Y direction. If there is water being withdrawn from the unconfined aquifer, then we have W of U. Now we have the leakage. So now the leakage, since it was basically going from the unconfined aquifer to the confined aquifer, this will act as a sink term. It's being removed. Whereas in the previous equation, since we are looking at the bottom aquifer, it is being added. So if it's a source for one aquifer, it's going to act as a sink for the adjoining aquifer then. And then you have the storage terms for the aquifer storativity and the specific yield for the unconfined aquifer. This is the change in the water table height as a function of time. So two equations and two unknowns. But this begins to give you an idea of how we try to set up the governing equations that one would have to work with for confined and unconfined aquifers, if you have leakage, if you have recharge, if you have water being withdrawn, and so on. Any questions? All right, so let's look at some, before we go to looking at some simple cases. So we use these kinds of governing equations to essentially model groundwater flow. And so for regional planning, in other words, how do we plan water resources? How do we plan how much pumping can occur and so on? So we rely on these mathematical models to help us do that. And even for local level planning to figure out what is going to happen with pumping from each individual well or what is happening in the neighborhood, we can do it. If it's a large area, typically we use Cartesian coordinates. If it's a single well, or if we are very much interested in what is happening with wells, and if the problem has, well, typically we assume it has radial symmetry, we essentially use radial coordinates, which we will see later. And then we try to solve those equations. We prefer analytical solutions, but analytical solutions will require some assumptions from idealizations, but nevertheless, they give us insights into the problem. Otherwise, you have to resort to numerical solutions. And depending on the complexity of the problem, complexity of the geometry, how large it is, how heterogeneous the aquifer is, and so on, your data requirements would be large, and the computer effort involved would also be large. And if you cannot idealize your real world to be close enough so that you get analytical solutions, then you have to resort to numerical methods. So let's talk about some simple cases. Let's say we are talking about one-dimensional flow in a confined aquifer. So one-dimensional flow in a confined aquifer, let's say x is in my direction, so the y coordinate, the y terms are not there, and I have this particular equation then to work with. T is the transmissivity, which could be a function of x. S is aquifer storativity, that could also be a function of x. And in simple cases, let's say when with steady state, so del H del T is 0. And if it's a homogeneous aquifer, that means capital T and W are not going to be dependent on x. It's homogeneous and they are constant. Then, of course, this equation simplifies to this simple second order equation. T times d square h dx squared minus W equals 0. We can integrate it twice. We get two constants of integration. And then the values of C1 and C2 would have to be determined based on what boundary conditions we use. So at two locations, or let's say we need two end conditions. So we need to have two more pieces of information which allow us to specify what the form of this solution is going to be. And those end conditions are going to determine what C1 and C2 are going to be. So the typical kinds of boundary conditions that we come across is one of the Dirichlet boundary condition. That means our state variable unknown is directly assigned. So let's say the piezometric head is known at a given location. And then that acts as a boundary. And that would be a Dirichlet condition. Sometimes the flux or the rate of flow or the derivative of H in this case is specified, let's say in terms of a specified flux or a specified Darcian flow, then you would use the Neumann boundary condition. You can have mixed conditions also, but these are two of the simpler boundary conditions. So for instance, in the same problem that we were looking at, if it's a confined aquifer, and let's say the head, the piezometric head, is constant at x equals 0, and we are given that at x equals L, there is a flux of Q given coming in. If these are given, then we have this particular equation for small h. At x equals 0, we would substitute that small h equals capital H. Okay. So small h would become capital H, x is 0, so these terms will disappear, and we would have evaluated one of the constants, C2. If the flow is given at a certain location, as in this case, then from this expression for H, you can calculate what the flow is going to be. It's minus transmissivity times dH dx. And from this equation, then we would estimate that, substitute that at x equals L, this value is given as Q. So minus capital T dH dx would be known to us. And we would use that, come back to this equation, substitute that as well to find out what C1 is, knowing that C2 is already obtained. So we substitute the values of C1 and C2, and then we would get an expression for H. And we would determine how H is varying with X, and we would make sure that it is satisfying the boundary conditions. That's the general strategy for simple cases. But this is the method that we use, for finding analytical solutions. One always needs to check that the boundary conditions and solutions make physical sense, because this is just a mathematical expression. It is not, so it's just a mathematical expression. It doesn't have to conform to what makes physical sense. It's up to us to interpret and make it conform to physical sense. If you apply boundary conditions, that means at x equals 0 and at x equals L, for instance, it means that this solution is only valid when x is between 0 and L. It doesn't tell you anything about what the piezometric head is at values of x less than 0 or values of x greater than L. That's what the idea of having those boundary conditions means. So, we do have to, there is some interpretation that goes along, with looking at a mathematical solution. You will see more of this, in some of the later lectures. If it's an unconfined aquifer, 1D again, and we'll talk about steady flow, our 1D equation would look like this, just based on what we talked about. Just that the terms in y have disappeared. We are essentially looking at flow in the x direction. It's steady state, that means this term over here is going to vanish. Homogeneous, so k is going to be constant, so it can come out. Okay. And we are assuming that w is constant, so it doesn't change with location. So constant withdrawal rate, let's say. In which case, since k comes out, we will have this particular equation. Now, as we recall, this equation, because we have a h del h del x, is linear in h squared, so we make this transformation, phi equals h squared, and we essentially get this revised equation, but that's linear in phi. And therefore, we can integrate this equation twice and get an expression for phi. Again, we have two constants, C1 and C2, and we'll have to be given two pieces of information, either about H or the fluxes or something that allows us to evaluate C1 and C2. And then that would be our solution for phi, which is we know to be h squared. Of course, once we know phi, square root of phi would give us the height of the water table in this case. And then we would basically do these kinds of simple problems using this particular kind of strategy. Any questions? Okay. So the utility of the equations, of course, is, we haven't talked about well hydraulics. Now that will come a little bit later. So one problem is what we call the power problem. So given aquifer properties, in this case, given transmissivity, and in principle, given storativity, given the right boundary conditions, right initial conditions if needed, we basically try to figure out what the head is going to be at different locations at future times, what the fluxes are going to be at different locations at different times. They're basically solving the governing differential equations. That's a power problem. The inverse problem is essentially us trying to identify the aquifer parameters. So we basically observe the value of the piezometric head at one or multiple locations as a function of time for given stresses to the system. So we apply pumping and so on. So we measure those quantities and try to infer what the transmissivity or the storativity should be based on our theory, so that our observations and model simulations look as close as possible. So that is our inverse problem. So for both of these, whether it's a power problem or whether it's an inverse problem, we will make use of these equations to help us do this. So the first part for today, we are going to stop over here, see if you have any questions. You'll also get a chance to sort of confirm your understanding of this in our tutorials today afternoon. But any questions? All right. I think the next part of the lecture will be done, or you'll be in very capable hands of Professor Hariprasad. But is there a break in between the two? Any questions before we go for a break? If not, we'll take the break now. Resume. When do you want us to come back? It's 11:15 now. So we start at 11:30.
Sir, may I ask a small question?
Yeah, of course.
Sir, if linearization is not giving accurate result, then what should be done?
If linearization doesn't work, then you have to either resort to numerical solutions, or you have to use some more advanced method. But typically, you have to deal with numerical solutions. All right. Okay.